Hello everyone. So we have discussed random variables so far. Now we are going to introduce the probability distributions and distribution functions. Before entering into random variables, we have also studied probability measures separately. Now we are going to combine these two things. Okay. So far what we know about random variables is that we can define a random variable x from say omega script a to r script b. Okay, so random variable takes inputs from omega and outputs are real numbers. And in general, when you have studied random variables and their probability distributions, you know that we always talk of something like PDF at some real number x, or PMF at some real number x, or CDF at some real number x. Okay. And when we studied probability measure in this course, we have studied about probability measure on this left hand side, that is probability of sets in omega, probability of subsets of omega, or the sets in script A. Okay. So today we are going to connect all these things. So how do I come to this type of scenario? How do I come to probability of real numbers? So let me consider some Borel set. So let S be a Borel set. So we know S consists of real numbers and we want to define something like probability of x belonging to S. Right. This is what we know when we say we want to know the probability distribution of a random variable. Okay. So probability of x belonging to S, this we will denote by Pxs. Okay. Pxs will denote we'll use the notation Pxs. So probability of x belonging to S is same as probability of x inverse of S. Am I right? If you are not clear, let me write one more step. So probability of x belonging to S is same as probability of all those omegas, set of all those omegas such that x of omega is in S. And this notation is nothing but for x inverse of S. Okay. And x inverse of S we know is in script A, because that is my definition of x being a random variable, that every Borel set should have inverse image in script A. Okay. And we know when we studied probability measure P was defined on every set in script A. Okay. So this is done. Okay. So this we already know. Hence, if we know the probability measure. Hence, Pxs is defined as probability of x inverse S if P is a probability measure defined on omega. Okay, omega script A. This Pxs is also known as induced probability measure. Okay, so this is known as induced probability measure or probability measure induced by x. So let us take one example. Okay. Let us take some example. We'll take a simple experiment, tossing of two coins. So the experiment is tossing two coins, and let me define random variable x as number of heads. Okay, so x is defined as number of heads, and let us assume that the coin is unbiased. Two unbiased coins. So what we know is probability of any of these. So probability of HH is 1 by 4. Probability of HT is 1 by 4. Similarly, probability of TH and TT are also 1 by 4. So each of these has equal contribution. Okay. And we want to compute, or we want to state what is the induced probability measure. Okay. So Pxs. Now let me first write down what are the possible values of x. So x can take value 0, 1, 2. So x takes value 0 if omega is equal to tt. So there are no heads, right? X takes value 1 if omega belongs to either ht or th. And x takes value 2 if omega is equal to hh. Okay. So it means that given any Borel set, we will have to check whether these three values, either 0 or 1 or 2, belong to that Borel set. Okay. So let me consider singleton 0 as a Borel set. So my definition would be Px of S, that is Px of singleton 0 would be probability of x inverse of singleton 0. And x inverse of singleton 0 is what? X inverse of singleton 0 is just tt. So this we know is 1 by 4. Okay. Instead of this, suppose I want to compute probability of closed interval 0, 1. Okay. So Px of 0, 1 closed interval. So 0 and 1 both belong to S. So this is probability of x inverse of 0, 1. And we know x inverse of 0, 1 would be, because 0 and 1 both are there, it would be ht, th and tt. ht, th for 1 and tt for 0. So this becomes 3 by 4. Okay. In this way, given any Borel set, we will check which of the three numbers 0, 1 and 2 belong to that Borel set, and depending on that we will get inverse image and hence probability. So what we have known is now, what we know now is, if we know probability measure on omega script A, we can compute the induced probability measure Pxs for any random variable x defined on omega script A. Okay. Now, the next part is to show that induced probability measure is also actually a probability measure. If we are calling it probability measure, we should show that it's a probability measure. Okay. So, induced probability measure is a probability measure. We will try to prove this. What do I mean by this? What I mean is, it should satisfy all the three conditions from definition of probability. So what were the conditions? First, it should always be non-negative. Secondly, when you input entire universal set in it, it should give you 1. And for disjoint sets, it should be additive. Okay. So we need to prove three things. We need to prove Pxs is greater than or equal to 0 for every S, is a probability measure on, let me write, probability measure on RB. Okay, Pxs is a probability measure on RB. So Pxs is greater than or equal to 0 for every B. Second is Px of entire R should be 1. And the third is if S1, S2 is a sequence of disjoint sets, then Px of union Si is same as sum over Px Si. This is the third thing we need to prove. I greater than or equal to 1. Okay, it can be countable union. Is it okay? Is it clear what all we need to prove? So let us try to prove this. The proof is actually just rewriting what we know, so it's not difficult. So first thing we want to prove is Px of S is greater than or equal to 0. Now what we know, Px of S is probability of x inverse of S, and P we already know is a probability measure. So it is probability of some set A for some A in script A, because that is my definition of a random variable. And we know that P is a probability measure on omega script A. So this is always greater than or equal to 0, because P is a probability measure. We don't know whether Px is a probability measure, that we are trying to prove, but we do know that P is a probability measure. So we are going to use it. Okay. Second property. So we want to compute what is Px of R. By definition, it would be probability of x inverse of R, and x inverse of entire R would become omega, because inverse image of entire real line means all possible values of x are already in that set. So we will need all possible omegas in that set. So it is P of omega, and again, since P is a probability measure on omega, we know this is 1. Okay. And the third is Px of union Si. So this we would write as probability of x inverse of union Si. Somewhere we need to mention that Si's are disjoint. So we know Si's are disjoint, and now if Si's are disjoint, then we also know that their inverses are also disjoint. Their inverse images are also disjoint. Okay. So this can be written as probability of union of x inverse of Si, and these are also disjoint. We have studied this property already. And because these are now disjoint, and union of disjoint sets is probability of union of disjoint sets is same as sum over the probabilities, it becomes sum over probability of x inverse of Si, and this is nothing but sum over probabilities of some AIs, and AIs are disjoint. Okay. So we have proved that probability. Okay, so this we'll need to rewrite. Probability of x inverse of Si I can write as Px of Si. Okay, probability of individual x inverse Si is same as Px of Si. So we have proved that Px of union Si is same as sum over Px of Si. Okay, hence Px becomes a probability measure on RBP. Okay, so what is the conclusion? Conclusion is, if I have omega script A with a probability measure P on it, and if X is defined from omega script A to RB, then RBPX becomes a probability space where Px is defined in a way we defined earlier. Okay. So if this is a probability space, and if we have a random variable, we can get a new probability space. Okay. Now next we have to talk about distribution functions, that is CDF. Now that we know how to define probabilities of different sets, we can define probabilities of intervals. Okay. So let X defined from omega script A to RB be a random variable. Okay, so let capital Fx be defined as probability of x belonging to minus infinity to small x closed. Okay, minus infinity to small x closed, which is same as probability of x being less than or equal to small x. Okay, this is nothing but Px of the interval minus infinity to x. Okay, now we can write either in terms of Px or P because we know their relationship. So this is known as distribution function. And what are the properties? The properties are, first of all, it is non-negative. Since it is probability, it is non-negative, so fx is always non-negative. Then second property is fx is non-decreasing. We can easily prove it. You take two arguments a and b, a less than b, and f of b minus f of a would be probability of the interval ab. Open closed will have to adjust, and hence since it is probability, it would always be greater than or equal to 0. So f of b minus f of a will always be greater than or equal to 0. Hence fx is non-decreasing. Third property is fx is right continuous. It is easy to prove this using the definition, and we have studied the properties of intervals, how union and intersection of intervals behave, so we can consider that. And fourth property is limit x going to minus infinity fx is 0, and limit x going to plus infinity fx is 1. We can use continuity of probability measures to prove this. Okay, every standard book has these proofs and they are quite easy to understand, so I am not going into the details here. Okay, so fx is a distribution function. Now fx has many interesting properties, and one of them is that given a random variable x, fx can be defined uniquely. Okay, and the other property is, if you know fx, then you can construct a random variable which would have this distribution function fx. Okay, so how do you do that? So for that we need to know what is meant by restriction and extension of functions. Okay, so let me define the two things. We will define in terms of general functions, and then we'll use it for the distribution functions. So suppose I have two sets such that one is subset of other. So let me call this as set A and this as, say, set B. So B is subset of A. And let me consider two functions f and g. Okay, suppose f is defined from A to R and g is defined from B to R. And in addition to that, what I have is f of small b is equal to g of small b for every small b in capital B. Okay, by the way, these A and B they are general sets. Okay, this B is not a Borel set or anything. So what we know is, we are saying that these two functions agree on the smaller set. Okay, and on the larger set, anyway the g function is not defined, whereas A is defined on the larger set. Okay, so in such a scenario, we say that f is an extension of g to A. Okay, we say that f is an extension of g to A because they were matching on a smaller set. Now you add few more arguments and you define a new function. So it becomes an extension of g to A. And similarly, we can say g is a restriction of f to A. Okay, g is defined on a smaller set in such a way that f and g agree. Okay, so g is a restriction of f to A. So, okay, now this we are going to use while defining CDF of any random variable or constructing a random variable which has that particular CDF. Okay, so we need two results. First result says that if C is a class of sets then the probability measure defined on C can be extended uniquely to a minimal field generated by C. Now we are going to need the definition of field. We know field consists of unions and intersections of sets. Here we are saying minimal field generated by C. So what we are going to do is, C is my class of sets, and now I will make it a field, means I will add unions and intersections of sets from C. So if I know probability of every set in C, of course I can uniquely define probabilities of unions and intersections of those sets, because we know what happens to probability of union, what happens to probability of intersection. Okay. As a result, I can uniquely extend the probability measure to minimal field generated by C. Uniquely extend means there is no doubt. There is no two values. So if two people try to extend, both of them will assign same values of probability to the additional sets. Okay. And then there is one more very important theorem, which is known as Kerr-Theodore extension theorem. So this Kerr-Theodore extension theorem says that from minimal field you can further go to minimal sigma field. Okay. So this says that if F is a field with some probability measure P, not script P, then the probability measure can be uniquely extended to the minimal sigma field generated by F. Okay, we won't go into the proof of this, but now we are going from field to sigma field. Okay, and that can also be done in a unique way. Now, see, when we know CDF, can we get uniquely the probability distribution of X? Yes, because we know CDF means we know f of X, that is probability of X less than or equal to X for every X. So given any Borel set, so probability of X belonging to any S can be written easily in terms of these intervals, because we know that these types of intervals minus infinity to X, they can generate an entire Borel sigma field. Okay, so that is the key in both these proofs, means saying that distribution function of any random variable is unique, and also that given a distribution function you can construct a random variable which will have that distribution. Okay, so as I said, if you know probabilities of minus infinity to X, it is same as knowing CDF. Okay, so knowing CDF is same as knowing probabilities of intervals minus infinity to X. The first result says you can extend it to field, and the Kerr-Theodore extension theorem says you can extend it to minimal sigma field. So minimal sigma field here is entire Borel set. Okay, so hence from CDF you can directly go to probability of every Borel set. Okay, and uniquely. So if you know CDF, you know the distribution of a random variable. Reverse way is a homework. Try to think. It's not difficult. Try to think how to go from CDF to a if you know that there exists some CDF which satisfies those properties, how to construct X which would have that distribution. Okay, how to construct X which would have F as CDF. That is your homework. Okay, I'll stop here.